Okay, let's continue. We started to look at periodic properties in the last class, and the first property we looked at were the atomic radii, and we have seen that the atomic radii depend on the position of the element within the periodic table. And we've also discussed about what are the trends that we can see. Now, another periodic property which is important is the first ionization energy of the elements. So let's quickly review what is meant by the first ionization energy. It's the energy required to remove the first electron from an atom. Okay? That means that can also be higher ionization energy. So we remove a second electron from an atom, assuming that atom has that second electron. We call this the second ionization energy, and so forth. So what we first should notice is that ionization energies are always positive. That means the removal of an electron from a neutral atom is always an endothermic process. It has to be like that because otherwise our atom would be stable. Firstly, we should notice that the ionization energy always reflects to an atom in the gas phase. Okay, that means an atom which doesn't make any interactions to its neighbor. So we always look at an isolated atom when we talk about ionization energy. So now, what are the trends in first ionization energies that we can see here? So we see here the ionization energies as a function of the periodic position of the periodic table. And here we see also the ionization energies listed as a function of the atomic numbers. So let's first see how ionization energies change within a period as we go from the left to the right in the periodic table within a period. So we can do this for the first period as we go from hydrogen to helium. We see that our ionization energy increases. So now, what about the second period? So it's a little hard to see here, but we also see that there is an increase in ionization energy. We can actually see this more clearly from this graph here. So as we go from the lithium to the neon, across the period, we see that the ionization energy increases. Okay, so we see the same is true as we go from the sodium to the argon. Okay, and then from the potassium to the krypton, and also from the rubidium to the xenon, and from the cesium to the radon. So this establishes the first trend that we can see. So ionization energy increases with the atomic number within a period. So the question is, how can we explain this? We can explain this again with the help of the effective nuclear charge. The effective nuclear charge increases within a period. For that reason, our electrons are being held more strongly to the nucleus, and that means that it's harder to move these electrons from an atom. So when we look at it closer, though, then we see that that trend, while it exists, is also sometimes broken. Okay, so for instance, when you look here within the second period, we see actually that there are two exceptions. So we see that the beryllium has a higher ionization energy than the boron, and we see that unexpectedly the nitrogen has a higher ionization energy than the oxygen. Okay. When we look into the third period, we see that here again, the magnesium has a higher ionization energy than the aluminum, and that the phosphorus has a higher ionization energy than the sulfur. So if we look further down the periodic table, looking at higher periods, we see again the same trend. So the elements of group 2 and group 15 have higher ionization energies as expected. Okay. Now we can again think about what made the explanation for that. And when we look at the group 2 elements, then we realize that, well, in a group 2 element, we have a full subshell. The S valence subshell is being full. Okay. Whereas when we go to the third group, okay, we have to start a new p shell. Okay. So it is therefore unusually hard to remove an electron from the full 2 subshell. Okay, because of which the ionization energy, first ionization energy for elements in the group 2 are higher than the ionization energy in the group 3. Okay, in group 13. Not 3, 13. Sorry, mistake. 13, not 3. It's the third main group, but the 13th group overall. Then for the group 15 elements, we can apply similar explanation. So for the group 15 elements, we have a half-filled p shell in which all electrons are in different p orbitals and they're all pointing spin up according to the Kunz rule. And that also represents a particular stable electron configuration. For that reason, the ionization energy is unusually high. So this explains why the trend is broken 2 times. Okay, for the group 2 and for the group 15 elements. Okay. So a few more things are noteworthy. So you see that within the main group elements, we see that the ionization energy actually increases fairly strongly as we go to the left to the right, as we go from the left to the right. However, from the first group onward, where we have D elements to consider also, we find that, well, in principle, there's also a similar trend, okay, but the ionization energy increases far less steeply in comparison to the main group. It's only slightly, it's almost constant. So we can also see if we can find an explanation for that. Now, when we have a transition metals, then we do not fill additional electrons into the outmost shell, okay, which would be the fourth shell for the first transition metal series. In the fourth period, we actually add the electrons to the underlying 3D shells, okay, and there the electrons can shield significantly better, okay, so they can significantly can much better shield the effective nuclear charge, and for that reason, by now the nucleus cannot pull the outmost electrons, which are still 4s electrons, so tightly to the nucleus and bind them that strongly. For that reason, we are seeing here a far less steep increase. Okay, so now the same argument you can also apply for the F block elements. You see there's hardly any increase in ionization ionization energy, and the reason is the same. We fill actually the new electrons not to the outermost shell, but to an inner shell, an inner F shell. There, the electrons can shield much better, and for that reason, it's actually easier to move the electrons by comparison. Hence, the ionization energy is actually larger. See that the effect for the F block elements is even stronger than for the D block elements. Okay, so there's one thing which is noteworthy, which is that there's an anomaly in the first group. Okay, so as we go down the first group, we see that there's a huge jump or a huge decrease. Maybe I should explain this in a moment, because now here we are going down a group, we're not going across the period. So now let's look at the second trend, which is that whenever we start a new period, our ionization energy drops sharply. Okay, so for instance, from the helium to the lithium, we see a sharp drop. And as we go from the neon to the potassium, we see a sharp drop. And the same happens when we go from the argon to the potassium. So that's, again, pretty easy to explain. When we start a new period, we start a new shell, we add that electron to a higher shell that's a lot further away from the nucleus. It experiences significantly smaller effective nuclear charge, hence it can be moved much more easily, and the ionization energy is much lower. Okay, so then there's again a third trend, which is basically the addition of the first and the second trend, which is that generally as we go down a group, the ionization energy tends to decline. Okay, you see this here for the first group and for the second group, and you see this holds as strictly also for all the other main groups. Okay, so we can explain this by the fact that the third trend is the sum of the previous two. However, you see there's one exception, which is that there's a big drop, a very big drop from the hydrogen to the lithium. You never see such a big drop in any other group. And that is because the hydrogen is unique in the sense that it has no other electrons that could shield the one electron. Okay, so for all other elements, this is no longer true, and for that reason, it is much harder to remove the electron from the hydrogen in comparison to the lithium and the higher alkyl metals. Okay, then let us move on to the next periodic trend, which is the electron affinity. So the electron affinity is the energy required or released to add an electron to a gaseous neutral atom. Okay? So again, we are adding an electron. So we are looking at an atom in the gas phase here. In this case, we measure the energy required or released to add an electron to that neutral atom. So as opposed to the ionization energy, the electron affinity can either be positive or negative. So the process can either be endothermic or exothermic. Okay. Now, unfortunately, with regard to the electron affinity, there's a little bit of confusion with regards to the algebraic sign, which has to do with that the concept of electron affinity was invented by physicists, and the concept of ionization energy was developed by chemists. So to a chemist, well, A negative energy is always associated with something exothermic, okay? And a positive energy is also something endothermic, whereas not necessarily so by physicists. So because electron affinity, the positive electron affinity would intuitively argue for a positive algebraic sign. You can find in the literature often that a positive electron affinity is associated with an exothermic process which corresponds to a spontaneous addition of the electron to an atom. Okay? However, this is inconsistent with how it's defined for the ionization energy. Therefore, now also in the literature, you can find that a negative electron affinity is associated with an exothermic process, which would mean that negative electron affinity means that the electron is added spontaneously to the atom. And it's actually, well, described like this in this table here. So in this table, a negative electron affinity here measured in kilojoules per mole means that the addition of the electron to the atom is actually exothermic and happens spontaneously. Okay, we do not require energy to make that process happen. So now when you look at this table here, you see that in contrast to the ionization energy, the process for the associated with the electron affinity can either be exothermic or endothermic. In most cases, it's exothermic, but occasionally it's also endothermic. Okay, so for all these elements below this line here, it's endothermic. And according to this definition here, the electron affinity is positive. And all these elements here have electron affinities associated with negative, with an exothermic process. Okay, so now let's look closer which elements actually tend to have electron affinities which are associated with an endothermic process. And you see that certainly all the noble gases belong to that group. And you can easily understand why. Noble gases have the noble gas electron configuration, which is very stable. If you wanted to add an electron to a neutral noble gas atom, we have to add that electron to a new shell, which would certainly be highly unfavorable. Okay. In addition to that, you see also, for instance, that for the beryllium, we have an endothermic process for the nitrogen, for instance, for the magnesium again, but also, for instance, for the cadmium, and also for the mercury. Okay, so in this case, we either have full subshells or we have half-filled subshells. So in the case of the nitrogen, for instance, we have a half-filled subshell for the neutral atom. Okay? So adding that electron to this very stable half-filled subshell is energetically not favorable. Okay? Hence, it's an endothermic process. So for the beryllium, the same. In this case, we have a full S subshell. In the case of magnesium, we have a full S subshell. In the case of the zinc, for instance, we have a full D subshell. The same for the cadmium and also for the mercury. And this explains pretty much all exceptions. Okay. But for all other cases, adding an electron to a neutral atom is an exothermic process. So can we see any trends? In this case, it's far more difficult to see any trends. but there are some weak trends. So generally, we see that the electron affinity becomes more negative according to this definition as we go from the left to the right within a group. So for instance, within a period, so for instance, here in the second period, we see that while this overall an increase starting from the lithium to the fluorine, but the trend is broken, and we already know the exceptions. Okay, for the nitrogen it's broken, as well as for the beryllium it's broken. But you see, the trend only continues to the fluorine. Okay, as we go to fluorine to the neon, we get a steep decrease, which we also know why. Okay, so again, we have a trend, but the trend has exceptions for certain reasons. Now, do we also see big jumps? Now, in this case, you see that we get the biggest jumps as we go from the group 17 to the group 18 elements. Okay, from the fluorine to the neon, from the chlorine to the argon, from the bromine to the kryptonite, and so forth. And again, we can explain why. For the halogen atoms, we have favorable conditions for the addition of an electron, okay, because we create a noble gas electron configuration. If we start out with a noble gas, then the addition of a further electron, of course, is very unfavorable energetically, because we would have to start a new shell. So as we look at the electron affinity being a function of the group, we see that there is actually not a clear trend to see. So, for instance, for the P block, we see that we see first an increase and then a decrease of electron affinity here. The same you see, for instance, also for the group 16, as you from oxygen to sulfur, we see an increase, but then we see a slight decrease. So for the S block, we actually see that as we go from the lithium to the sodium, where's the sodium? We see a decline. As we go from the sodium to the potassium, we see another little bit decline. So for these, actually, the electron affinity decreases or becomes somewhat less exothermic. For the D block elements, you cannot actually see any particular trend. So there are basically too many factors that influence the electron affinity, which would go beyond scope to explain here. So overall, electron affinity shows far weaker trends than the ionization energy, but one can find some. All right. So the last periodic property that I wanted to, yes, question.
Yeah, just to clarify, would a greater electron affinity be more negative or more positive? Like if you say something has a greater electron affinity.
Yeah, as I said before, there's a confusion with the algebraic sign. Okay. So when we talk about affinity, we mean that a positive affinity is always something which attracts something, and that was the original definition of electron affinity. Okay, but the algebraic sign is inconsistent with the definition of exothermic and endothermic. Therefore, you always need to basically say how you define your algebraic sign according to which definition.
Could you repeat what you said about the half-filled subshells and how that affects the trend? And how that relates to electron?
Yes. So whenever an element has a full subshell, or half-fold subshell, then that represents a pretty stable electron configuration. So in this case, it's energetically unfavorable to add an electron to the neutral atom. Okay, that means our electron affinity would be low according to the original definition, or we would say that basically adding an electron would be an endothermic process with a positive algebraic sign. Whenever we move a neutral atom out of a favorable electron configuration, then that leads to low electron affinity associated with an endothermic process. Yes.
So according to this sign convention, are there any cases where an ionization energy would be exothermic?
Ionization energies are always endothermic. So with regard to ionization energy, you don't have that problem with algebraic sign definition. So it's clear cut. All right. Then I wanted to discuss the last periodic property, which is the electronegativity. So electronegativity is sounds similar, but is clearly to be distinguished from electron affinity. So electronegativity is the measure of the ability of an atom to attract electrons within a chemical bond. Okay. So again, the ability of an atom to attract electrons is being measured, and this is similar to the electron affinity. When we're talking about the electron affinity, we look at an isolated atom. And we're talking about the electronegativity, we mean an atom within a chemical compound that is actually making chemical bonds to other atoms, not an isolated. So the concept of electronegativity is one of the most useful concepts in chemistry because it can explain so much about chemical bonding, and has originally been developed in order to explain polarity in chemical compounds. And this original work has been done by Linus Pauling, and he also developed the first electronegativity scale, which related bond polarity to electronegativity and related differences in bond energies to bond polarity and electronegativity. So basically, he said that, well, when we break up homoleptic bonds, okay, for instance, AA and BB, to make heteroleptic bonds AB, okay, then the energy difference between the heteroleptic bonds and the homoleptic bonds, or the average of the homoleptic bonds, okay, translates into a polarity within the bond, okay, which relates to an electronegativity difference between these elements, which would be defined as the ability of these elements to attract electrons within a chemical bond. Okay, so low electronegativity would mean low ability to attract the electron in the chemical bond. Okay, and high electronegativity would mean high ability to do the same. Okay. Now first he actually used the arithmetic means of the homoleptic bond energies, and later on he used the geometric means, just because it appeared to work better. And the geometric means is nothing else but the product of the homoleptic bond energies, okay, to the square root. Okay, this is how the geometric means is defined, and you just subtract this this average energy from the energy of the heteroleptic bonds, and that energy then relates to an electronegative difference between the two elements. So now you can easily see that from this definition, we can only get electronegativity differences, but not absolute electronegativity values that we could assign to a particular element. Okay, so because of that, the entire electronegativity scale needs a reference point. Okay, Pauling defined fluorine as a reference element and assigned arbitrarily the value of 4.0, and the electronegativity of all the other elements would then be referenced to the electronegativity of fluorine. Okay, so now you see here the periodic table with all the Pauling electronegativity scales. First of all, what is eye-catching is that the noble gases don't have electronegativity values. Why is that? Because noble gases make hardly any compounds. And of course, bond dissociation energies will require compounds to be present. Okay, but noble gases hardly make any compounds. Okay, especially not with homoleptic bonds. Okay, so you can't make anything which has an argon-argon bond. It's just not possible, and therefore you can't measure any bond dissociation. For that reason, noble gases, there's no electronegativity value on the Pauling scale. Okay, but for all the other elements, you can assign electronegativity values. So fluorine has the highest electronegativity value, and all the other elements have smaller values. So what periodic trends can we actually see here? So as we go across a period, we can see that with increasing atomic number within a period, the electronegativity increases. And in contrast to the ionization energy, this trend is never broken. So we get actually continuous increase of electronegativity as we go from the left to the right in the periodic table without any exceptions. So again, as we start a new period, we see that there is a sharp drop in electronegativity, okay, whereby we cannot account for the noble gases here. So basically, we have to go from fluorine to the sodium, and we see a big drop. As we go from the chlorine to the potassium, again, we see a big drop because we go from the bromine to the rubidium. We also see a big drop. And as a third trend, we can see that the electronegativity tends to decrease as we go down a group. This trend actually holds strictly for the main group elements. So you see for the first group here, for instance, we see a decrease in electronegativity here. For the second group, it's true. And also for all the main group, other main group elements, this trend holds true. It's just that for the transition metals, there's not such a clear trend. We see actually that the highest the metals with the highest electronegativities are noble metals, in particular gold. So gold is the metal with the highest electronegativity. If you look at the value, it's actually 2.4. You see that is a value similar to some non-metals, for instance, like iodine, yeah, or also phosphorus or sulfur have similar electronegativity values. That actually has the consequence that gold in some circumstances behaves more like a non-metal, like a metal in particular, when combined with an element that has a very low electronegativity. Okay, because then you have a very large electronegativity difference. And we know that from previous courses that compounds that have a very high electronegativity difference tend to be ionic. So if you combine actually gold with cesium to make a compound CSAU, which is an intermetallic compound, then unexpectedly that compound doesn't show metallic behavior, but it actually is an ionic transparent crystal. That's because of the high electronegativity difference between the cesium and the gold. Okay. So overall, cesium is also the element that has the lowest electronegativity value. Essentially, that's because electronegativity increases from the left to the right in the periodic table, but tends to decrease as we go down a particular group. Okay, so this is the concept of electronegativity and the Pauling scale. So now the Pauling electronegativity scale was empirically derived from bond dissociation energies, but it has not been derived from the quantum mechanical model of the atom and other periodic properties. So therefore, scientists after Pauling have tried to devise other electronegativity scales that would take other periodic properties and the quantum mechanical model of the atom into account and make the electronegativity scales less empirical and put them on a more theoretical basis. And there are a few of them that I would like to discuss. So the first very common used electronegativity scale is the scale of Oret and Rojo. And in the Oret-Rojo scale, the electronegativity is a function of the effective nuclear charge over the radius of the atom square. The effective nuclear charge over radius square relates actually to a Coulomb force experienced by an electron on the surface of an atom. So the Coulomb force increases with the effective nuclear charge, and it decreases with the radius square. Okay, intuitively, we would understand that the Coulomb force on the surface of an atom would relate to the electronegativity, because the higher that Coulomb force is, the more ability the atom would have to attract electrons to it in a chemical bond. So here you see that there are two other numbers here, 3,590, which is basically a coefficient to this term here. And we have 0.744 added to this term over here. So these terms are actually empirically found. They actually just there in order to make the electronegativity scale comparable to the Pauling scale, which was first, just so that it gives similar numbers so that one can have more easier comparison. Okay, so this is just basically experimental an empirical fit to make a comparison of the two scales easier. So another very popular scale is the Mulliken scale. So the Mulliken scale relates electronegativity to two other periodic properties, namely the ionization energy and the electron affinity. So it basically says that the higher the ionization energy is, the harder it is to move an electron from neutral atom. And the higher the electron affinity is, which basically means the ease to add a new electron to a neutral atom, the higher the electronegativity is. Okay, and again, there are factors 1.118 and minus 0.217. Again, these are in order to make the Mulliken scale compatible to the with a Pauli scale. Okay, so you see that there's of course a relationship between Mulliken and Rojo, because previously we have discussed that the effective nuclear charge can be explained, can be used to explain ionization energies. Okay. It can also be used in order to explain electron affinities. Therefore, we are not all that surprised that the Mulliken scale works in addition to the Rojo scale. So the last one that I would like to discuss is that of Reed and CR. This is not an exhaustive list. There are many more definitions, but these here are probably the most common ones, which says that the electronegativity is nothing else but the number of P and S electrons, or the energy, the energy of the P and the S electrons over their number. So basically, the electronegativity is correlated to the average energy of the P and S electron in an atom. Okay? And this concept of electronegativity is specifically applied to main group elements, because the main group elements, the sp electrons, are the valence electrons. Okay, so we again perhaps not all that surprised that this concept also works, which is because, well, we have learned that, well, the electron energies are actually related to the effective nuclear charge, which has been used to explain electronegativity according to Ord and Rojo. And so according to that, the lower these average electron energies are, I would expect more ability this element has to attract electrons from other atoms, also within chemical. Okay, so we are now actually finished with the definitions of electronegativity in scales. Now let us apply electronegativity to chemical bonding. And let us first apply electronegativity to chemical bonding within elements, and then let us apply electronegativity to chemical bonding in compounds. See if you can explain chemical bonding using the concept of electronegativity. So you see here again the periodic table, and in that periodic table you see that all the metals are here in blue, and all the non-metals here, they are green, and well, everything which is a metalloid is orange. And see underneath each element symbol, we have a value for the electronegativity value, for the electronegativity value. So now let us see if we can correlate the electronegativity to the chemical bonding within our elements. Okay, So what chemical bonding do we have within the metals? Metallic bonding, okay. So what chemical bonding do we have in the non-metals? Covalent bonding, correct. And within the metalloids here, we have actually something which is in between covalent and metallic bonding. Okay. So now let's look at the electronegativity values of the respective atoms. So we see that for the metalloids, the electronegativities tend to be all around 2, okay, 2.04, 1.9, 2.01, 2.18, 2.05, 2.1, 2.2. Okay. So for the non-metals, they tend to be significantly higher than 2. And for the metals, they tend to be significantly lower than 2, with some exceptions, like, for instance, the gold. Yeah? That is a general trend. We can say that when we have electronegativity values smaller than 2, then we would expect metallic bonding. And if we have electronegativity values significantly higher than 2, then likely there will be covalent bonding. If it's around 2, most likely there will be something in between. Okay. So now we can think about, can we extend this concept also to compounds? Okay, where we have chemical bonding in between different elements. Okay, within an element, I mean, chemical bonding is always between atoms of the same element, naturally. So where we would actually combine atoms of different electronegativities to make compounds. That can be nicely described by what is called Catalase Triangle. So in Catalase Triangle, you have 2 axes. On the x-axis here, you have the absolute electronegativity. We can also say that this is an average electronegativity of the atoms in the compound. It's nothing else but electronegativity of atom A plus electronegativity of atom B over 2. And here on that scale, in that direction on the y-axis, we have electronegativity difference between all 2 atoms. Okay. So here on the x-axis, of course, our electronegativity difference is 0. Therefore, all substances which are elements would actually lie here on our x-axis. Okay, and cesium would be most to the left because the element with the smallest electronegativity, and fluorine would be most to the right because it's the element that has the highest electronegativity. All the other elements would actually lie here in between. Okay. So now all compounds made of 2 different elements would have at least somewhat of an electronegative difference in between them, so they would lie above the y-axis. But within Ketelaar's triangle, okay? So cesium and fluorine build the first 2 corners of Ketelaar's triangle, but the third corner is defined by the compound cesium fluoride. And that is because in cesium fluoride, we have the greatest electronegativity difference in a compound that we can have. Yeah? That's because cesium is has the lowest electronegativity, fluorine is the highest. And that now implies that basically any other compound must lie within that triangle or at least on the edges. So on this edge here, we would have basically cesium compounds okay, that would increase in electronegativity difference as we go from cesium metal to cesium fluoride. And here on that edge, we would have only fluorine compounds, whereby the electronegativity difference in these fluorine compounds would increase as we go from this corner here on the edge to this corner. Okay, so for example, OF2 would lie close to F2, while lithium fluoride would lie close to cesium fluoride, because electronegativity difference between lithium and fluorine is much higher than that between oxygen. Okay. So all the other compounds would lie within this triangle. So now the corners of these triangles represent extreme bonding situations. Okay, so here in this corner we would have the most metallic situation. Here in this corner we would have the most covalent situation, and here in this corner we would have the most ionic situation. Okay, because here for cesium fluoride the electronegativity difference is the greatest. Okay, but you see that for the greatest majority of compounds, we have influences actually from all three bonding situations. In which one dominates depends on the exact position of our compound in Ketelaar's triangle. Okay, the closer it is to this corner, the more ionic. The closer it is to this corner, the more metallic, and the closer it is to that corner, the more covalent. Okay, so for instance, lithium oxide lies here. You see it's mostly ionic, but there's also small influences from covalency still, and even some degree of metallicity. Okay, remember that even if an ionic crystal, if you just apply voltage high enough, yeah, it will still become electrically conducting, because of which you can say, well, there's still also a little bit metallic bonding here. Because whereas, for instance, when you have a compound like SRMG, yeah, you see, well, it's pretty much metallic, but it's also not completely metallic. There's also some ionic character because of the electronegativity difference between strontium and magnesium. There's also some covalent component as well. So generally, we can say that we can actually make a completely covalent bond because electronegativity difference can be zero, but we cannot actually make a completely ionic bond because electronegativity difference is always finite. Yeah, it cannot be infinitely large. Therefore, even for the most ionic compound, we still have some degree of covalency and electron sharing. Okay, so overall, you can see that the concept of electronegativity can make very nice quantitative predictions with regards to whether we would expect a metallic compound, a covalent compound, or an ionic compound. All right, so that actually closes our first chapter about atomic structure. In the next class, we will continue with a new chapter about symmetry and the applications of symmetry to covalent bonds. So let's stop at this point and